Welcome to Peninsula Seniors Out and About. Today we're at the Western Museum of Flight in Torrance for one of their celebrity lectures. Let's go see what Cindy has for us today.
Welcome everyone to the Western Museum of Flight. I'm Cindy Maka, the director for the museum. Barry has granted us the privilege of sharing his encyclopedic knowledge with us before. At that time, we expected a fascinating and informative presentation. His talk certainly exceeded our expectations, and as a reward, he has the privilege of coming to speak to us again. Our reward is he has come to speak to us again. Ladies and gentlemen, back by popular demand, Barry Tyson.
Thank you very much, Cindy, and thank everybody for coming. It should be a pretty interesting discussion. Many of you know the big aerospace companies in Southern California: Northrop, Douglas, Lockheed, North American. But there's a company called Garrett AiResearch. If you worked at any of the big aerospace companies, you know Garrett AiResearch because we supplied you with most of your subsystems. If you worked for one of these companies, you never went wrong by selecting anything made by Garrett. It may not have been the cheapest, but it was definitely the best product. And the company was started by Cliff Garrett back in the 1930s, and Cliff started as a manufacturer's rep, an industrial supply salesman, dealing with all of the aerospace companies. And I think that gave him a feel for what the big contractors really wanted, how to work with the customer, how to please the customer, and that extended forward for the rest of the company's history. Before we really get going, I'll tell you about me. Like many in Southern California, I came here from New York, have a degree from New York University in aeronautical engineering. My first job was at Douglas Aircraft El Segundo, working in the aerothermal group. Thermal was not my best subject. I was terrified. Fortunately, it had nothing to do with thermodynamics, everything to do with integrating aircraft and engines. I got a master's degree at USC in 1963, and when I thought Douglas wasn't really doing too well and I had just gotten married, I went down to Ryan in San Diego. Very few people knew about Ryan. You know, everybody knows they built the Spirit of St. Louis, but what have they done lately? But in the 65 to 75 time period, Ryan turned out over 1,000 drones. One of them is on display at the museum for use in the Vietnam War. They did high altitude and low altitude photo reconnaissance. They did intelligence gathering. To my knowledge, unless it hit somebody in the head, the drones never killed anybody. But after working at Ryan for about 10 years, my last program involved using a Garrett engine on a large unmanned aircraft, the predecessor to Global Hawk. It was called Compass Cope, and I really fell in love with the engineers at Garrett. Now there I was living in La Jolla, California. Gorgeous spot, right? January 1976, 80 degrees. I had decided to join Garrett. The job assignment, Dayton, Ohio. We drove to Dayton. It was 26 below zero when we got there, and that was my commitment to the Garrett Corporation. 3 years later, I had a call. Would I like to go to Phoenix and run military propulsion sales? It was kind of a no-brainer, so I said, absolutely. So I joined the Phoenix division. I rose up to Vice President of Sales and came over to Los Angeles, where I got into business development and strategic planning. So I've been with Garrett for about 22 years and spent 20 years before that as an engineer. Cliff Garrett was an entrepreneurial visionary. He started back in the 30s, used turbocharging experience as a springboard to other product lines that I'll talk about in a minute. Under Cliff's leadership, the company and its divisions had many firsts in the aerospace industry. The first all-aluminum intercooler on the B-17, cabin pressure regulators, 1941, the first light aircraft turboprop engine, and the first gas turbine APU on passenger aircraft. This is my opinion of Garrett's business principles. Garrett wanted to become number one in all of its selected businesses. They also wanted businesses with high cost of entry, businesses where it was hard for competitors to get involved. It was technology driven. As I said earlier, it may not be the cheapest, but definitely it was the best. And they're systems oriented. If they build a valve, why not build a control for the valve? Why not build a thing that the valve controls? Let's keep expanding what we can do. They had a very powerful sales and service organization, which was the customer's voice. It was split into two parts. One was called government relations, and this is where Garrett got prime contracts from the Army, the Navy, the Air Force, NASA, to do the technologies that we needed for our commercial and military products. I worked in government relations in the Dayton office covering Wright-Patterson and NASA in Cleveland. They also had a field sales organization. These engineers were salespeople who lived with our customers. And often when we had pricing meetings, they were the voice of the customer and competitive intelligence at these meetings. You know, you're driven on the one hand to keep the price low, and on the other hand to come up with new and better technology. And that balance was something that the sales organization really was responsible for doing. We'll start with turbochargers because, as the title of my presentation said, it's from turbochargers to afterburners. We used to do, maybe we still do, 30,000 turbochargers every single day. Started in 1936. We had over 6,000 employees, and you can see in the upper right a picture of an Audi RL16 which won Le Mans with a Garrett turbocharger. A lot of our business is for Caterpillar, International Harvester, heavy truck engines, but all of the automobile manufacturers. You don't have to look at the details of a turbocharger. I show this only to illustrate that there were some key technologies involved. Heat transfer, turbo machinery, control systems, a knowledge of materials, how far can you push them from a temperature and pressure standpoint, actuation, and valves. And these technologies were at the heart of most of the products we built. Some of them are on display at the museum, others we'll talk about as propulsion engines. Now the businesses of Garrett are very complex, and I tried to simplify it for this meeting. Let's look at three locations: Torrance, California, Phoenix, Arizona, and Tucson. Torrance, California is where we did environmental control systems for commercial and military aircraft and space power, life support systems. We did electrical power generation, electromechanical actuation, and the automotive turbochargers. In Arizona, we did propulsion and APU, pneumatic systems, and airline service and support. In Tucson, we did electronic controls and cabin pressure control systems. What I haven't shown on this chart is the interrelationship between the various divisions. So Torrance might be responsible for the environmental control on a new transport, but they'll acquire their valve technology from Tempe, Arizona. They'll acquire the control technology, digital electronic controls, from Tucson, Arizona. And so the companies played with each other. Let's talk about propulsion and auxiliary power. Back in the early 70s, business aviation was served by mostly three jet engine manufacturers. There was Pratt & Whitney with an old JT-12. GE had a commercial version of the J-85 called the CJ-610. And Rolls-Royce had an engine called the Viper 20. And those engines were turbojets, pure and simple, very thirsty. Newer general aviation aircraft using turboprops were on the horizon. Also, airlines were looking at the hub-spoke concept where 19-passenger regionals were becoming popular. There was a market for 19-passenger commuters. Turbofan jet commuters were also being considered, as well as primary flight trainers. All of those were markets for new generation of turbofan and turboprop engines. The auxiliary power market comprised ground carts, commercial transports, military transports, The interesting thing we'll talk about in a little bit is that with twin-engine transports like the 777, extended range over the ocean, having an APU as backup power was instrumental to getting that approval. Then there's the helicopter engine market. And when Allied Signal or Honeywell acquired Lycoming, that brought a huge influx of helicopter engines. I'm going to have a lot of charts, courtesy of my friend in Phoenix, Jean-Paul Frignac, our resident Frenchman, who presented this at a Gas Turbine Institute paper. One quick story about JP. He's called JP. We happened to fly together to my one and only Paris Air Show in 1983. And as you go through customs, they scan your passports. I got through, he didn't. He was pulled aside. And later I said, JP, what was the problem? And he said, well, they can't believe anybody in their right mind would give up French citizenship to become an American. So that was the delay. From 1945, Garrett started playing with something called a black box. In 1948, the first successful gas turbine entered production, and in 1952, the gas turbine facility is moved to Phoenix. On APUs, they provide starting power for the main engines, pneumatic power for environmental control systems. They drive pneumatic and hydraulic systems and backup electrical power, and they do ground operations. So when an airplane wheels into a hangar for ground maintenance, if it's the winter time, the people cleaning it will hit the APU and get heating. If it's summertime, they'll hit the APU and get air conditioning, so they work in a shirt sleeve environment, courtesy of the APU. We have 20 basic models and over 150 applications, and we've shipped over 64,000 of these. Let's take a look at how they're used. The 85 series was the first APU to be put on a commercial transport. It was a Boeing 727 in 1963. I think Boeing's concept was the 727 was to operate from remote fields. These fields didn't have a lot of ground-based facilities. With the onboard APU, they could start the main engines, they could provide heating or air conditioning. It was self-sufficient. The 331 series, the first application for which was the Boeing 777. So in-flight operability allows extended twin-engine flight operations. You can see that the largest APU is on the 747. We'll talk about that in a little bit because it became the backbone for the Garrett Turbofan engine. Let's talk about turboprops. A market for turboprops began to emerge in the late 60s. Piston engines were topping out in power. Gas turbine opportunities were there for helicopters and fixed-wing aircraft. Garrett had a contract from the Army to build a dual-purpose generator set, 400 shaft horsepower. It had a lightweight, rugged, low-cost design, and so that became the core of a turboprop. The first customer was North American for the counterinsurgency aircraft, the OV-10. From that beginning, the series TPE turboprop engine 331 family spanned the range from 500 to 1,500 horsepower, a very simple design, a very successful design. And today, there are over 13,000 engines delivered, 92 million flight hours, and this may be difficult to see, but this is a list of aircraft that use the Garrett turboprop. Here are some you might be familiar with: family, the Mitsubishi, the Rockwell Commander, the Cessna Conquest, and a Beech King Air model. This was my favorite. We convinced Piper to put a 1,500 shaft horsepower engine on a Cheyenne 400, and they advertised it as the 400-mile-an-hour turboprop. And in fact, I think its cruise speed at sea level was about 330 knots, and we derated it from 1,500 to 1,000 horsepower. But this little baby used to go between Tucson and Los Angeles, and they only sold 45 of these aircraft, but sure would be nice to own one. I'd mentioned 19-passenger commuters. These were a few of the airplanes that we powered: the Swearingen Metro, the Jetstream 41, the Dornier 228. Now we'll go into turbofan propulsion. In the mid-60s, people were looking at turbofan engines to provide higher thrust, lower fuel consumption, lower noise around heavily populated airports. And the first business jets, as I mentioned, were powered by very fuel-thirsty, old-style jet engines. And it was the right time for Garrett to enter this market. We had the DC-10 APU. And so we had the idea that we can adapt that core as a turbofan. And the person interested in doing that was Ed Swearingen, who talked to us about his vision of creating a transonic business jet. And he needed 2,700 pounds of thrust. So being an entrepreneurial company with infinite budget, we decided, let's go for it. It didn't pan out. However, before we get into what works, let's get a little education here. Does everybody know the difference between a low pressure and a high pressure compressor, between an axial and a centrifugal turbine? Do you know what a bypass ratio is? So turbofan engines, we talk about bypass ratio. There's a certain amount of incoming air which bypasses the core, never gets burned. It exits through the fan duct. The remainder goes through the core. The ratio of the airflow that doesn't get burned to the air that does get burned is called a bypass ratio. Now, why is this popular? We all know that at low speed, propellers are very efficient. As the slipstream velocity approaches your flight speed, efficiency goes to 100%. But if you go faster, you can't have large propellers powering fast airplanes because the drag of the nacelle installation would kill you. So an engine like this is a compromise. The cold air coming out the fan mixes with the hot exhaust gas, reducing the average jet velocity and reducing the fuel consumption, increasing the efficiency of the engine. That's the principle of the turbofan, and I invite you to look at the display that we have in the museum of the 731-5. It's a cutaway, and you can see all this. So here's the 731-2 at 3,500 pounds of thrust. Bypass ratio on this family of engine goes from 3 to 5, has a full authority electronic fuel control, fairly simple design. The unique part of it is it has a geared fan. Now, when Garrett first talked about having a fan driven by a gear, people thought we were crazy. The reason for the gear is that the core rotates at very high speed. If you had the fan go at the same speed, the Mach number of the tips of the fan would be so high, shock waves would form, the efficiency would be down. So you need to gear down the RPM of the fan, and that's what we did. And I was interested to note that Pratt & Whitney's latest engine for a 130-passenger Bombardier airplane uses a geared turbofan. Learjet and Dassault were the first customers. We had the French connection to bring Dassault, which was very good. And so we built the 731-2, but based now on the Boeing 747 APU. That APU gulped more air, hence gave more thrust than the DC-10 APU. Here are some airplanes powered by the Garrett 731 engine. We've sold over 11,000 engines with 100+ million flight hours, over 40 aircraft applications. And interesting to you taxpayers, it's probably the only engine in civil service that didn't start as a military or as an airline engine. Here are some airplanes that you might see around on the flight line: the Learjet, Cessna, Westwind, Falcon, Hawker. An interesting point on this chart is that there is a marriage between the engine supplier and the airframe contractor. If you own an airplane today, your next airplane will probably be bigger, or fly faster, or fly higher. And so you'll come to the engine guy and say, I need a bigger engine. And so the engine guy thinks dollar signs. It's a lot of money to do that. Is it really necessary? But you have to do it, or the airframer will drop you in favor of a competitor. So the history of growth of all of these manufacturers and their product line matches the history of growth in the Garrett engine product line. But because engines were getting more expensive to develop, we looked for ways to do joint ventures. And the first one that came along was with GE on an engine called the CFE 738. That engine had 6,000 pounds of thrust. Garrett did the low pressure core and GE did the high pressure core. It was installed in the Falcon 2000, and And what I remember about our corporate pilots telling me is that you could load that airplane up with anything it would carry and fly nonstop coast to coast. You never had to worry about weight and balance. Just stuff everything in there, take off and go. It was a great airplane. First flight in 1994. Now we'll go into military propulsion programs. Very unusual program was started because of the conflict between Red China and Taiwan. The People's Republic of China is Red China, and Republic of China is Taiwan. Senator Goldwater of Arizona, because we worked in Arizona, was interested in not rocking the boat anymore with People's Republic of China because we were supporting their Air Force. Northrop had T-38s over there. Northrop helped them do the logistics program. How could we make Taiwan self-sufficient in aircraft? And so Garrett had started working with Volvo Fligmotor on an afterburning engine we call the model TFE 1042. We finished the program with ITEC, International Turbine Engine Company, which basically was Taiwanese engineers. They all came to Phoenix, and they worked in the basement of our engineering building, and together they designed with our engineers a low bypass ratio afterburning engine for a fighter. A dry version, a non-afterburning version of that engine was called the F-124, which found its way into trainers. I'll tell you one interesting story. Taiwan needed an airframe company to design their fighter, and they selected General Dynamics Fort Worth. We had an engineer working in sales. He had a PhD, I think, from Caltech. He was Chinese, and he wanted to join sales, and the only opening we had was in Dallas, Fort Worth. And we knew he was single, and he wanted a girlfriend. And we said, David, if we put you in Fort Worth, you'll never run into a Chinese girl. It's not going to happen. He said, but I want to go. The next time we went out there, General Dynamics had announced that they were the partner with Taiwan, and we saw David in a restaurant surrounded by Chinese engineers, all wearing cowboy hats, cutting into their steaks, and he was God. He could speak English, he could speak Chinese. They worshiped this guy. He later married, not one of the engineers. So here's an example of the non-afterburning engine flying in a Taiwan trainer. Now we show a Czechoslovakian trainer. And so they have over 1 million hours in service right now on that non-afterburning engine. This is, was my first program in Phoenix. Many of you who are Air Force pilots learned to fly in a T-37 with a Continental J-69 turbojet engine. The T-37s were getting very old. The J-69s were wearing out. They were very fuel thirsty. So the Air Force had an idea for what they call the next generation trainer. This trainer was going to be the first one to accommodate a female pilot. And so you had to design the cockpit to handle a 200-pound guy and a 100-pound girl. That was a problem. The engine was designed to a criteria they called NSIP, Engine Structural Integrity Program. The concept came from the way they were designing airplanes. If a crack occurred, you would presume that there was a crack that you didn't discover. How long would it take for that crack to propagate to a failure? Now you're going to inspect at half that interval. They carried that philosophy to an engine, which meant they wanted one hot section overhaul for the life of the airplane, which meant you had to keep the temperatures and pressures and stress levels low enough to be able to do that. What does that do to weight? What does that do to performance? What does that do to cost? It makes everything a little worse. We won the competition. And the competition was unusual in that the Air Force said, we'll let the airframe guys select the engine they want, and if they win the contest, we, the Air Force at Wright Field, will develop the engine for them. My first job was convincing the airframe companies that NSIP was what the Air Force wanted, because it made your development program expensive and it made the engine expensive. I convinced just about everybody, and we were sole source selected by all but one contractor as their engine. The winner of the competition was Fairchild Republic. Now, unfortunately, Republic ran into some difficulties. The airplane did not meet spec, and so the program was terminated, and what it cost Garrett was the chance to sell 600 engines F-109 engines. But not all was wasted, because we took the core of that engine and we turned it into a helicopter engine. But since Garrett didn't exactly have helicopter credentials, and the president of Allison had been a former Garrett engineer, we went to Allison and we said, whereas you guys build helicopter engines and whereas we have a core, let's get together. So we got together and we built an engine called the T-800, and the program was the Comanche light helicopter experimental. It was to replace the UH-1, the OH-1, a whole bunch of small helicopters for the U.S. Army. Program was canceled because of the peace dividend everybody expected. There went the F-109. Now we'll talk about unmanned programs. Here's an engine designed in Torrance called the Garrett ATF-3. Very unusual engine. The flow going through that had to make a couple of 300, maybe it was one 360-degree turn. It was a bypass ratio 3 engine, very strange looking, but it had some advantages. The advantages were it had a very high pressure ratio, very, very low fuel consumption, and that meant it could stay aloft at high altitude for long times. Guess what? The Air Force back in the 70s wanted a high-altitude, long-endurance surveillance airplane. Ryan bid the program called Compass Cope. We used a single Garrett ATF-3 engine. Very low infrared signature, because the gas was all mixed when it came out the back. We demonstrated 24 hours, unrefueled, at 55,000 feet, carrying a 750-pound payload. We flew successfully, did everything the Air Force wanted, and they decided to give the contract to Boeing. And that's when I joined Garrett and left San Diego for Dayton, Ohio. But the ATF-3 found another home. I didn't know about this till fairly recently, searching the internet for ATF-3s. Those of you who belong to the museum may recognize Steve Smith from Northrop. He was the chief engineer on an airplane called Tacit Blue, which was to demonstrate stealth technology. Getting back to my friend in Phoenix, J.P. Frignac, I said, J.P., were you read into this program? And he said when he mentioned it to his boss said, J.P., you still have parents in France. Forget all about it. And that was the end of it. So that was Tacit Blue, and it was to demonstrate stealth technology. This slide, the significance says that in 1995, we merged Lycoming into Allied signal engines. The picture of an airplane is, again, a Taiwanese trainer, the AT-3. Once Lycoming was part of the team, the fit was rather extensive. In blue, you can see the Garrett businesses. In tan or brown, you can see the Lycoming businesses. So it basically covered all market segments. Lycoming got its start from the German Junkers design team with funding from NASA, Wright Field, and some German technology. First engine started in Williamsport, Pennsylvania, 600 horsepower engine, first flight in 1956. T-53 became one of the most successful engines ever built, over 19,000 built, powering the Mohawk and the Marine Cobra helicopter. Here's a picture of some of the aircraft you probably have seen powered by the T-53. Growth version was the T-55 engine at 2,200 horsepower for the Chinook heavy lift helicopter. You've all seen that helicopter, just seen a lot of active service. Lycoming took that core and converted it to a 7,500-pound thrust turbofan engine, the ALF 502, used on the BAE 146 and the Canadair Challenger. Also used on the Northrop A9. I believe we have an A9 airplane somewhere at the museum on display at the far end. The A9 lost the competition to, of course, the A10. A BAE transport engine contractors love it because it has 4 engines. A small helicopter engine is the LTS-101, 1,600 engines in service, over 6 million flying hours. and you can see some of the applications of that engine. So my conclusion is to show that over the years, the markets we now serve, business jets, fighters and trainers, commuters, utility aircraft, regional jets, and helicopters with a full spectrum of engines. Thank you very much. The question is, do we have any recent history of what's happening with propulsion engines at Honeywell today? I do know that Honeywell has its own HS series of turbofan engines that they're developing. I do not know, John, if we have found any customers yet for those engines, but they are larger because, as you know, the 19 passenger is passé, 30 passenger is becoming passé. The market demand is for 100 passenger and higher, which takes a larger engine, which puts us into real head-to-head competition with Rolls-Royce, Pratt, and GE. Any other questions? The question is, do we have an APU on the new Airbus A380? And I'm not sure, but I don't think we do. Does anybody in the audience know that for sure? Yes. Doug? We do not. The answer is we do not have an APU on the A380. The question is, do we have any marine applications for ships? Not to my knowledge. I don't think we make any propulsion units for ships. I'm not sure about auxiliary power. Does anybody know if we have auxiliary power units on Navy vessels? The question is, in view of the recent publicity of the Carnival Cruise Line problems, maybe putting an APU on board cruise lines is an interesting opportunity for Garrett. The question is, do we have any power on PT boats? I don't think we do. No marine propulsion. We did have the ATF-3 on a Coast Guard airplane, the HU-25, and ships are mostly found at sea level, and the engine was not designed to fly there, so salt air corrosion, salt water corrosion became a problem. Any other? Yes, sir. Question is, are we involved in the Super Cruise engines in any way? I think the direct answer is no. We did have an engineer working for us who came to us from United Technologies and who became a government consultant on supersonic combustion ramjets. But our company itself never really did get involved. Anyone else? Yes, sir. The question relates to centrifuges. Right, and that wasn't the propulsion business. That was a separate activity for Department of Energy. Yes, sir. You know, I retired in 1998, and I really haven't stayed current on what the company's doing in space systems. We do have people here who did work on early life support for the Gemini, the Apollo capsule. We did life support in outer space. And we also were talking about a Brayton cycle, solar Brayton cycle, for power on board satellites. But this goes way back to the 70s and 80s. I'm not really sure what we're doing today. Yes, sir. Chuck. The question is, could I say a few words about the turbocharger business, the automobile business? And I think, Chuck, I'm not the right guy to answer that. I think maybe the museum should have a separate presentation on turbochargers because it's a big enough subject to really justify its own presentation. Larry, question? The statement is that there's a multitude of subjects that we could do at the museum. For example, on display are segments from environmental control systems. We have people who can talk about environmental control systems, cabin pressurization, windshield de-icing systems. We have divisions that do ground proximity avoidance, crash survivable flight recorders, data recorders. We acquired Sunstrand, who used to make all that. These are all subjects fitting for their own discussions of itself. Yes, Dick. Walter's saying that the first turbochargers were done under license to General Electric. You know, if somebody really is interested, we have several people in the audience that could really go into turbochargers a heck of a lot better than I could. Walt, you want to come up and talk about turbochargers? You put your foot in it now. The question related to turbochargers, and we're fortunate to have in the audience a former AiResearch program manager on the F-16 emergency power unit, Walt Yeager, who can help answer the question.
I'll give you just a bit of a background. I actually started with Garrett on the ATF-3 program, which we started here. Worked on the fuel control system. And when the first major cutbacks came, I then went over to the Turbocharger division here on Lomita Boulevard. And I worked in sales for a little over a year. One of the biggest problems that we had with the turbochargers that were used on the small aircraft was the liability issues. Every time an airplane had a loss of power, it seemed that the Garrett Corporation got sued. And so I became what was called the Director of Product Integrity. And my primary job was to investigate all accidents and to assure our insurance company and our company that we were doing what we should from a safety standpoint, and to document that we weren't really at fault in these accidents, which to my knowledge we almost never had a problem. And we went from hundreds of millions of dollars in lawsuits to a couple of million, I think, when I left. And then I went back to manufacturing division on 190th Street, and there worked in Turbo Machinery Group, and have been involved in emergency start system, emergency power units, and the emergency power unit over here was my favorite product. It's sitting right there on the table. But the question was about turbochargers. So let me get back to that. Of course, being in the division about turbochargers during its explosive growth period from 1971 through 1980, I got the background, of course, of where it started. The first production turbocharger that Garrett put on a car was, I think, a 1962 Buick engine that was used in an Oldsmobile. It was a small displacement V8 engine, fairly high compression, and it worked pretty good as long as you kept this water alcohol mix in a tank to keep the engine from going into detonation. So it was in production, I think, 2 years. It was called the T5, if I'm not mistaken. Then there were no automobile turbochargers except some kits that were built and sold. And there was a man here in Southern California that sold a kit for a Pinto. And they used a regular, as a matter of fact, I was involved in the sale of the parts to him that he put in the kit. He ran into problems with getting the California Air Resources permission to modify the induction and exhaust systems on the engine. And he proved that the emissions were far less than a production unit. That didn't matter. He said it'd take a few $1,000s to help him get that approved, which kind of we know what that might mean. So that program didn't go too well, but several people were working on a production version of a small turbocharger, and I believe the Buick 3.8 liter V6 was turbocharged about 1976 or somewhere along in there. And there were quite a number of those built. The biggest complaint with the car was that it had turbo lag. When you hit the accelerator, nothing happened initially, but boy, when it did come on, it ran great. So The lady that was here last week, Maxine, was involved with a development of ceramic turbine wheel, and a ceramic turbine wheel weighs what, 1/4 of what the Inconel or whatever it is, the standard material is, and those would accelerate much better. And so the Grand National Buick had a turbocharger from Garrett with a ceramic wheel, and they just blow your hat off. They accelerated so well by comparison. That was the point at which suddenly turbocharging became very well adopted. I think it was the Mustang 4-cylinder Ford was then a first high volume. I believe that was the first high volume, and there were many of those that were sold. It went through some growing pains. There were problems with the turbocharger wastegate that controlled the speed, and that was worked out. And I guess millions of them have been developed over the years. Multiple turbos are used now. In order to have 2 small ones, they accelerate better than 1 big one. So anyway, it's still going on. You need somebody from Honeywell to come here to really tell you the last 10 years, because I retired in 1998 also.
Okay.
Thank you.
Well, thank you. Thank you.
Anything else?
Yeah. You'd like to know where Garrett was located prior to Torrance. Charlotte, where was Garrett located prior to Torrance? At the entrance to LAX, but I was thinking even before that, it was an office in Los Angeles, wasn't it? Yeah. Okay, any other question? All right, well, thank you very much. Okay. There were many questions that came up during the presentation about products built by AiResearch in Torrance. I have with me Dr. John Mason, who was our Vice President of Engineering, and is very familiar with the products we made, and here's John to talk about them.
Thank you, Barry. I'd like to start out by talking about air cycle refrigeration. This was one of the big company products starting in the early 1950s. It was found that instead of using Freon, a refrigerant in so-called vapor cycle compressors and air conditioning systems, air cycle was preferable. Instead of using the refrigerant like Freon, an air cycle machine takes the air, compresses it, and cools it and expands it. Now let's take a look at the hardware. Here's an example of a cooling turbine which is used in a large commercial transport aircraft, one of the Boeing aircraft. This is the same kind of machine used in a smaller airplane, probably a fighter aircraft. I'm not sure just which airplane it is. But a key point is that each one of these turbo machines is the heart of the air cycle air conditioning system. And in this kind of system, the most important component is the cooling turbine, which furnishes cold air to the cabin. This works by expanding compressed air, and in the expansion process, the air is cooled and the cold air goes into the cabin. And the beauty of this is you can have small leaks and there's no problem, which is a plus in maintenance. And one of the things that Garrett did as a pioneer was so-called air bearings in this machine, and I'll point to them. Here are the bearings that use no lubricant at all and will run forever. In the meantime, the failure of this kind of a machine is of the order of 250,000 to 500,000 hours. The final thing I'd like to talk about that's on display here is an emergency auxiliary power unit. And this too was one of the big product lines of the AiResearch Los Angeles plant. These were made initially as power units for missiles, and then more recently emergency power units for aircraft. And typically they will use a monopropellant. And a large supply isn't necessary because these emergency units have to run for only a few minutes, but they'll use a stored propellant. In this case, this one uses hydrazine. And a hydrazine fuel is a so-called monofuel, which put in contact with the catalyst will decompose and produce hot gases. Hydrazine produces a mixture of nitrogen and ammonia, I believe, when it decomposes. And the idea is it's hot gas under high pressure, and the hot gas will drive a generator or a hydraulic pump or something else that keeps the airplane flying in an emergency case. And if you remember the event that took place in the Hudson River in New York a few years ago, emergency power was absolutely essential. That plus the skill of the pilot saved all of those people. Thank you very much.
Thank you, John, for sharing that with our audience. Thank you very much.
My pleasure.
Thank you for watching Peninsula Seniors Out and About here at the Western Museum of Flight in Torrance. I'm Betty Wheaton. I'll see you next time.